Topic 5 is called energetics and thermochemistry. So we are going to be looking at the energy that is occurring within reactions. Topic 5.1 is actually going to be split into two different videos. The first one is just looking at the basic information of what energetics is and introducing you to thermochemistry and the basics. If you've taken physics, you've probably actually seen a lot of this information. And then the second video that I split out really goes into the calculations we need to do when performing chemical reactions in a lab. First, the unit's called energetics. So what is that? Well, energy means the measure of ability to do work. You all should have taken physics at this point, and you've done an energy unit. That is not separate from what we are doing here. Physics just looks at a much larger region of work and energy. We are looking at the energy and work done in a chemical reaction specifically. The breaking and the forming of bonds, if energy is being released or if it's being absorbed, what's going where, so we can predict the effect that reaction is going to have. So in chemistry, we look a lot more specifically at what's going on. Different forms of energy that can be looked at in chemistry and physics, but by no means is a comprehensive list, are heat, light, sound, electricity, and chemical energy. We specifically are going to be looking at that heat aspect. So, what is heat? Heat is the mode of energy transfer due to temperature difference and produces an increase in disorder or entropy in how particles behave. So we know as we add more heat to a system that you are going to increase the movement of the particles, and therefore you are increasing this disorder or entropy, which is actually discussed in 15.2. If you take temperature away from particles, they're going to become much more ordered, and they change most like through state changes towards that solid state, crystalline state, so on and so forth. You guys should have covered that last year or within your sophomore year of chemistry. Now, looking at what's going to occur, where the reaction's taking place, and where this energy of transfer is going to be. We have our system and we have our surroundings. So what are each of these? The system is going to be the area of interest. So this is if we're having a reaction. So we have our beaker, right? And in our beaker, we have our reaction taking place. And here, so we have water and we have two aqueous solutions, so on and so forth. This area where the reaction is taking place, that is our system. Surroundings is everything else. So surroundings is going to be anywhere that the reaction is not taking place. So all the atmosphere, the glass, whatever it is, the reaction is taking place, that is where the surroundings are. In chemistry, we have two different types of systems, and we can even look at this biologically or physically, but looking at chemistry and where reactions are taking place. If we're running a lab, you need to know whether you're running an open system or a closed system. An open system is where energy and matter can exchange with the surroundings easily. So you don't have a lid on your beaker. There's nothing keeping everything within this reaction itself. That is the most time what we have to do just because of what we have available for us. And a closed system means that that system can exchange energy, because energy is not matter. It can go between the walls of the glass in this atmosphere or the copper piping or whatever it is. Energy can transfer, but not the matter. The matter is trapped within the system itself. Closed is going to be an ideal reaction. That way we're controlling everything but the energy being exchanged. Reality, even though we tried the best, open is where we tend to be. And so when we talk about errors and loss of energy, looking at theoretical yields and stuff like that, that's because we can't get a perfectly closed system within our laboratory. Now, when we look at this and we look at what energy is and what's being transferred to and from, it is only the systems and it's only the surroundings we're looking at. So the system may be giving energy to the surroundings, or the surroundings may be given to the system, and it's always looking at that relationship to them. And so one thing we need to keep in mind is total energy is the same. So the system's loss is the surroundings gain. The surroundings loss is the system's gain. Because of the law of conservation of energy, there is always, you can't just lose it. It is going to be conserved. It's going to be somewhere, and it's just where is it going to be? In chemistry, we call this whole process enthalpy. So you may hear me say energy, you may hear me say enthalpy. It is the same term, essentially. Enthalpy is just the more politically chemistry correct term in relation to heat and where that heat is going, but you can use those two terms interchangeably. So enthalpy is the heat content of a substance. So every substance we know has stored energy. We call that potential energy, and that's where this physics comes in. What we are going to be working at with throughout this entire unit is what we call delta H. And that delta, as you should know, it means change. And H means heat. So the change in heat. And that is what we are going to be spending the majority of this entire unit on, is looking at where is the heat at. Now, when we're looking at the enthalpy of a substance, we're looking at the total energy in the system. And where's that energy going to come from? It's going to come from stored bonds. So when you have two atoms together, there is energy available in that bond. And so when the bond breaks or when it forms, there's going to be energy released or absorbed. And also when you have particles that are close, or actual compounds close to each other, you have those IMFs. And remember, those IMFs can be your van der Waals forces, also known as London dispersion forces. They can be your dipole forces, your dipole-dipole, and they could be hydrogen bonds. And the stronger the IMF, the more total energy you have in your system. Okay? So we also look at that interaction between compounds, and we look at it within a compound. All of that's going to affect how much energy it takes to break and or form a bond and run a chemical reaction. So we have two types of reactions, exothermic reactions and endothermic reactions. Looking at exothermic reactions first. This is when you have a transfer of heat from your system to the surroundings. So if we have our beaker, and inside our beaker we have our reaction taking place. And because we're looking at energy, and the way we specifically measure energy is going to be temperature, we have our thermometer in there. And we are going to look at, is the temperature going to increase or decrease? Well, since this is an exothermic reaction, that means the energy in the reaction is going to be going from the system, so from the reaction, out into the surroundings. Think of it as an exit. XO, exit. Energy is exiting. Therefore, heat is leaving. We would see a decrease in temperature. Exothermic reactions actually consist of most chemical reactions, including all combustion, which is your hydrocarbons plus excess oxygen makes CO2 and H2O, and neutralization reactions where we have an acid and a base and we neutralize it into usually salt and a water. Here is an example of what an exothermic reaction looks like. You've seen reactions before. So here we have methane is reacting with 2 oxygen to make 1 carbon dioxide and 2 waters. That should be, you should be used to that. It's on the right-hand side. That is what is new to us. So we have our delta H, and as we saw before, delta H means the change in heat. So where is the heat going? Looking at these numbers, or looking at this value, there's a couple things. So here we have a negative sign. That negative sign means that energy, or it's showing the direction of energy. If it's negative, energy is leaving the system. If it's positive, it's moving into the system. Then we have our value. So that is the value of energy movement. We have 809. And lastly, we have the unit, kilojoules per mole. Now remember, in IB, we don't use the slash, we use the inverse. So we quite literally write Kj moles -1. And so this is looking at the energy, and kilojoules is the energy, or the unit of energy, as you have learned in physics, per mole of the reactant you are looking at. Specifically looking over in this reaction, the reactant we are looking at is methane. So we're looking at per mole of methane. So as you can see, we have 1 mole of methane, and that is going to be very consistent across all the reactions we look at. We want to look at per mole. But what happens if this is 2 moles instead of 1? Well, that means the delta H change should multiply by 2 as well, because everything happens per mole. And so keep that in mind. IB does ask questions where they put a 2 in front of their choice reactant, and that changes the value. And so you really need to look at everything we do in this energetics unit is going to be per mole of the substance we are looking at. Now we have something called an enthalpy change or enthalpy level diagram. You probably have seen these before actually in biology. So we have our chart. On our y-axis we have delta H, or we have enthalpy. You may even see it written as energy. On the bottom essentially is time, but we just simplify it into the reaction taking place. If we are in exothermic reaction, that means energy is leaving the system. So we need to know where they're going to be at. And so this is very general. So we have our reactants. And our reactants have a lot of stored energy because they're going to be losing that energy. And then we have our products. All right? And so when you draw these diagrams, reactants are less stable than our products because since our products have less energy, they're going to be more stable, less likely to react. Now, in all reactions, with the exception of spontaneous reactions, you actually need to give that reaction a kickstart. And we do that a lot of time by heating up a reaction to speed it up. So we draw this hump, and then we go straight down into our products. This hump right here, hopefully this is all review for you, right there, that is called your activation energy. So we write it as EA. So activation energy, how much energy we need to activate the reaction, to push the reaction forward. And that's going to differ depending on the stability of those reactants. Now, what if we put a catalyst in? And so a catalyst does not change the direction of the reaction. It does not change how many reactants are there or how many products we make, but it decreases your activation energy. So if we put in a catalyst, that lowers your activation energy. And so it's easier for the reactants to go to products. And that just allows us to make the reaction faster. All right, endothermic reactions. This is when you have energy transfer from the surroundings to the system. So if we go back to our beaker, and we have our reaction taking place, purple's so much more fun, and we have our thermometer in that reaction, right? Well, in exothermic reaction, heat was exiting. In endothermic reaction, heat's coming in. And so we have heat out here, and it's going to go into the system. And these are much more rare and harder to do. And you'll see why on the enthalpy level diagram. So there are fewer reactions that fall into the endothermic category due to the reactants being more stable than your products. And so if we go back and we look at our enthalpy level diagram, right? So here we have our delta H. Here we have the reaction taking place. And if we know energy is going into the system, that means the reactants are low and the products are high. And so you need a specific situation where we want to go towards more unstable products, which doesn't make sense in the terms of thermodynamics where everything goes towards disorder instead of towards order or towards more stored energy. When we draw this, we still have to draw that hump. That activation energy is a lot higher to go up, and we can still have a catalyst, so we don't need to put as much energy into the system to get the reaction to go forward. A classic example of an endothermic reaction is photosynthesis. So we have CO2 and H2O is making 1 mole of what we want to make, and that is going to be glucose with our O2. Now, if you look at our delta H again, remember here's where energetics is lying, is over here with this value. Instead of a negative, we have a positive. Okay, that positive means that that energy is going into the system. Now you can see with this value, it's so much higher than methane. So you can see that this more complex compound C6H12O6 has much more stored energy than methane CH4. So you can see that complexity of the molecule, more bonds the molecule has, more energy potential it has as well. But the unit's the same because we're still looking at 1 mole of whatever it is we are making in the systems, because in endothermic reactions, we're looking at the products. So when we're running a reaction, we have our standard enthalpy changes. And this is going to be delta H, and because remember, delta is the change in energy, H is enthalpy. This theta right here, whenever you see that, that means we're going under standard conditions. What are those standard conditions? If you're working with a gas, and only a gas, does pressure affect it? So that means we're working at 100 kPa, kilopascals. You don't have to have that necessarily memorized because it is in your data booklet. If we're working with a solution, the concentration is 1.0 moles per decimeter cubed. And so all solutions have that concentration. The substances need to be in their standard state. So gas, liquid, or solid, that you either just know it will be given to you, or you can actually find it in your reference sections within your data booklet. And the temperature is going to be at 298 Kelvin. We will always work with Kelvin within energetics. It is the absolute scale, and we'll discuss why in a later video. So we're going to look at a simple calculation first. First, we need to know what's going on. We're working with energy. Energy we measure with temperature. So temperature is the measure of average kinetic energy. The unit in which we use this is Kelvin, also known as capital K. And this is going to emphasize the relationship between the average kinetic energy within your solution, your reaction, gases, whatever it is you're working with, and the temperature being read on the thermometer. We're looking at that change in that temperature. So the change in temperature depends on the mass of the object. More mass of an object, that means quite literally you have just more there. And therefore you have more stored potential energy, therefore you should see more of a change. We will never work with a whole lot, of course, just because of cost, but you can make that direct relationship. How much heat is going to be added, especially if we're heating up a reaction to try to push it forward, so on and so forth, if you're adding fire or flames, anything along those lines. The amount of heat added to the reaction is going to change the way the temperature is affected within the reaction itself. And then the nature of the substance. We are going to see this in multiple topics this year. And the nature of the substance is quite literally, what do the IMFs look like? Is it an ionic compound? Is it a covalent compound? If it's a covalent compound, what type of force does it have? Is it hydrogen bonds? Is it van der Waals forces? Is it dipole-dipole interactions? You need to be able to identify the strength of the bond and the strength of the IMFs in order to predict how much energy is going to be associated in the stored energy of that substance. We have two types of simple calculations we're looking at. The one we are going to use most often is called specific heat capacity. This is the heat needed to increase the temperature of a mass by 1 Kelvin. So the key term here is mass. We want to take the mass of an object. So 10 grams of copper, 20 grams of water, whatever it happens to be. Okay, we want to know how much heat it takes to increase that mass by 1 Kelvin. The reaction looks like this. Heat change, and that is Q, equals the mass of the object we're looking at times the specific heat capacity, so that's known as C, and that will either be given to you in the data booklet or you're going to be solving for it, and times the change in temperature. We call this the MCAT calculation, so MC delta, which looks like an AT, so MCAT. Then we're going to be looking, or you could look at just the heat capacity in general. So this is the heat needed to increase the temperature of an object by 1 Kelvin. So we're not looking at the mass of an object, we're just looking at an object itself. And this helps us to distinguish the relationship between different objects. So if we have a swimming pool versus an open lake, or we have asphalt versus concrete, they're not the same mass, and therefore there are all multiple different compounds present, and it's not just one compound because it's specific heat capacity. It's specific to one compound. If we're looking at something that has a mixture in it, we can't be specific, so we can only look at the heat capacity itself. So this is a little bit more simple, where you have heat capacity, so you have C equals the heat change, which we can measure with a thermometer, over the change in temperature. So essentially, and this is big C, sorry, we are taking out that mass portion above. All right, so we're going to do a simple calculation. Okay, so if we have 10 grams of copper. Copper has a specific heat of 0.385 joules per gram per Kelvin. Oh, sorry. Per degree Celsius. The temperature change we notice during this reaction is we start at 85 degrees Celsius and we're going to go to 25 degrees Celsius. What is the heat change in this reaction? So what is Q? All right, so if we have Q equals MC delta T. For T, you can change these to Kelvin, or you can leave it in Celsius, because when you change something by 1 degree Celsius, you also change it by 1 Kelvin. So MCAT doesn't matter if you're using degrees Celsius or Kelvin, just understand that there is a direct relationship there. Quite literally, plug and chug. So we have a mass of our object, 10 grams, times its specific heat capacity, 0.385, times the change in temperature, so final minus initial, gives us negative 60 degrees Celsius. And when you go through and calculate that information, you get negative 231 joules of energy is the heat change that occurs. How do you change that to delta H, or sorry, kilojoules? If we want to change that to kilojoules, it becomes negative 0.231 kilojoules, because kilo is 1,000, so we take that decimal and move it 3 times.